All right, ladies and gentlemen, class recording for today has started. So, over the past week and a half, we've started talking about projectile motion. The big gist of projectile motion being we have these two motions that are occurring simultaneously, but they are independent of one another, right? There's a horizontal motion occurring, there's a vertical motion occurring, but they're both occurring at the same time, but they don't affect each other. And that means we can analyze each one of them separately and find out what we need to find out about the situation. So, yesterday, when we started talking about the slug shooting and making something a projectile, the initial problems that we did we called horizontal launch problems, where something, let me do this, let's say we had a table, all right, and then here's a floor. Okay. And let's say there's a ball that's rolling along the table and it hits the edge of the table, all right? At that moment, it comes under the influence of gravity and gravity only. And so it experiences a downward acceleration of 9.81. But because when it hit the edge of the table, it was already moving forward, it doesn't lose that forward motion. It continues doing that forward motion as gravity is causing it to fall down to the ground. And as a result, when it becomes a projectile under the influence of gravity, right, we end up moving in that parabolic path. Okay? So in this case here, because it starts at the highest point and it starts heading downward from there, because it was moving sideways when it became a projectile, right, we end up with half of a parabola. Okay? But what we want to look at, or what we started looking at in the slug shooting lab, and then what we're going to continue looking at today, is something that moves in a complete parabolic path, where it has an up and a down. Okay? And in order to do that, well, let's look at the problem. So it says, chipping from the rough, a golfer sends the ball over a 3-meter high tree that is 14 meters away. The ball lands, on the green of course, at the same level at which it was struck, after traveling a horizontal distance of 17.8. A, if the ball left the club at an angle of 54 degrees above the horizontal and landed on the green 2.24 seconds later, what was the initial speed? So let's start with that one, all right? Okay, first things first, all right? You guys have that, now pull back with that sheet as well, so that you feel around that, that's fine. So we're going to do a couple of problems. All right, so first things first, what is part A asking us for? Start with that. The initial speed, right? What was the initial speed? Okay. Now, here's where that gets a little tricky, okay? Unlike the problem of the ball rolling off the table, at this point, if we're going to go up first and then down, there has to be some vertical velocity, right, to cause us to go in that upward direction. So, you see on the sheet that I gave you today, this, over on the right-hand side up at the top, there are these two pictures. All right. These two pictures represent important concepts dealing with projectile motions. Let's start with the bottom one, okay? You'll see that the bottom one, labeled B there, the vector that's going in the middle is labeled as VI. That vector is labeled as VI, standing for the initial velocity. But, as we discussed with displacements a little earlier in the last unit, right? If we're traveling in a northwesterly direction, right? We're really doing two things at once. we're traveling north, and we're traveling west simultaneously. Is that good? Okay. The combination of that north motion and the west motion occurring simultaneously takes us in the northwesterly direction. The same thing is true in this case when the object becomes a projectile, when it starts being acted on by gravity and gravity only. That intermediate or middle vector is labeled as VI. But in order for something to be at an angle, there has to be two things going on at once. There has to be a horizontal motion and a vertical motion occurring simultaneously, the end result of which is we travel in that diagonal direction. Are we okay with that? Okay. Now, that only occurs at the very, very beginning of this projectile's path. When we exert that initial push or throw or whatever it is to make it start flying through the air. As soon as it leaves our hand, or as soon as it leaves, in the case of the problem we're doing here, the golf club, what's the only thing that's going to affect its motion? Gravity. Gravity will cause a change in the vertical velocity, but because gravity acts up and down, there's nothing to change the horizontal velocity. Does that make sense? So, when we put this arrow, right, for VI, or when we work with this arrow for VI, we're only talking about the very beginning of the flight. Once it leaves the golf club or your hand or whatever else launches it, it doesn't follow this path anymore. It follows this parabolic trajectory. All right? So that arrow for VI, we can see on the picture that's labeled A right above it, is just, that only applies at the very, very beginning of its flight. After that, it follows that parabolic path. Are we okay with that? Okay. So, getting back to the question at hand. Oh, there it is. When it says, what is the initial speed, it wants us to find what was that velocity right at the very, very beginning of the ball's flight. Now, when it's asking for speed, that means we don't have to concern ourselves with what? Direction. All we need to know is how fast it's going, right? And so, in the case of A, we want to know this, right? What is that speed? But, like we just talked about, and it's detailed on picture B up there on the right-hand side of the page, if something's going to be traveling in a diagonal direction, it has to be doing what simultaneously? The diagonal motion is a result of what? It's going up and sideways at the same time. Okay? So this resultant motion is really the combination of this and this. Okay? So if we're going to find the diagonal, we also have to know this one, and we have to know this one. Okay? Good with a plan of attack so far. All right, so let's figure out how we're going to get there. Okay? So we said, I told you yesterday, and it's still written on the board over on the right-hand side over there, even though you can't see it if you're watching the recording. If this is a projectile motion problem, right, where should we start? Any projectile motion problem should start with what? Well, before we do the acceleration, draw the three-column chart, right? So let's draw the three-column chart. Boom, boom, boom. All right? First column, right? All of the things that we use to measure motion. So VI, VF, A, T, delta X / Y. Second column horizontal, third column vertical. Okay? Good so far? All right. We said that there's one thing we can throw in right away, no matter what problem that we're doing, and that's what? Accelerations. The horizontal acceleration is always going to be what? 0. The vertical acceleration is going to be what? Negative 9.81. All right. Good there. Now, a little bit backwards, right? But let's fill in our question marks. Okay? What are we trying to solve for? That purple arrow that we are trying to find, the initial speed, occurs at the very beginning of the projectile's flight. But it's a combination of a horizontal motion and a vertical motion. So what are we really trying to fill in on the chart? Which row are we trying to find here? Initial velocity. And if we're going to find the initial resultant velocity, that means we need to know the initial horizontal velocity and the initial vertical velocity. Does that make sense? Okay with that? Okay, let's start filling in some other things. All right, John. Good. So it says here that it lands at the same level at which it was struck after traveling a horizontal distance of 17.8. So that's going to be my delta x. Okay? What else? Sean, go ahead. The time is going to be 2.24 seconds, right? It tells us that straight up. Okay. And then there's one more thing. It's one of those non-obvious things. Okay, so right now, Ben, we have it, like we said that in order to solve for one of the things in this chart, we need to know 3 other things, right? So horizontally, we're good so far, right? We can find what we need to find, right? There's one more piece of information I want to fill in, though, before we start doing calculations.
Delta y is 0.
Okay, delta y is 0. Do we understand why delta y is 0? Okay. What does it tell you about where the ball lands? The same plane that it started on, right? Even though it's traveled horizontally 17.8 meters, if it says at the same level at which it was struck, it goes up and it comes back down vertically, it's exactly where it started. Does that make sense? You okay with that? So that means that delta y is going to be 0. Yes, no, maybe. You okay with those things? All right. So now we have 3 pieces of information in each column. And that means we can solve for the thing that we need to solve for in each column. Okay? Horizontally, generally speaking, is going to be an easier calculation because the acceleration of 0 makes it pretty easy to do. Right? Vertically is a little bit more complex, but because of the numbers, it becomes a little bit easier. Okay? So why don't we take a couple minutes here and calculate VI horizontal and VI vertical. Go. the answer to this problem? No. Right? We talked about that at the beginning, this initial velocity is actually a combination of a horizontal velocity and a vertical velocity. We just went through and we found out what those horizontal and vertical velocities were, right? So now, right, with this, watch some color changes, right? This is now this, and this is now this. Does that make sense? Okay? I'm trying to keep my colors consistent to help us follow the flow of ideas. Okay? So now we have a diagonal that we're trying to find, but we know the horizontal and vertical. What are we going to use to get us to this, to find the diagonal? Pythagorean theorem, right? Even though this currently isn't a triangle, right? It's okay vector-wise if we go sideways first and then up, or if we go up and then sideways. At the end of the day, we're going to end up in the same spot. Does that make sense? Right? So we can rearrange these vectors to look something like this. That good? And we know that the horizontal velocity is 7.95. And we know the vertical velocity is 10.99. And now we've got two sides of a right triangle, and we can use Pythagorean theorem to find the third side. So let me go ahead and do that. And that's what I ended up with as far as the initial velocity of the golf ball. Okay. Does that make sense? So, does it make sense that this is the equation? Yeah. So for people watching the recording, right? That's the equation there, right? Yeah. Because delta y is 0, that whole side basically goes away. Okay? So I move this first term over to the other side. I have to subtract it because they're added together there, right? Okay? And now we have t on both sides. So one of my t's cancels on the right-hand side, one of the t on the left-hand side cancels, and that leaves us an equation that only has one unknown in it, that being vi. And then I just plugged in the things that we figured out from the problem. Because this is t squared, right? So this t cancels here, but only one of those t's cancels there, and we're only left with one t. Very good. Oh, yeah, sure, yeah, that's fine. So, yeah, I don't care how you do the math. That's up to you. Like, and quite frankly, when I'm grading the test, the math is like a small portion of the points that you can get. If you identify the variables, like the table in the top left, and then you pick the appropriate equation and plug the things in where they're supposed to be plugged in, that's most of your points when I'm grading. So, yeah. I'm trying to, what I'm doing a little bit more, is to do that manipulation algebraically with just the variables, with just the letters, because that shows up a lot on tests. where they just rearrange equations and say, okay, what is this, what is that, instead of plugging numbers in and being dependent on solving it that way, to go with the variables. So that's why I did it that way. All right, okay with this. Okay. Let's talk a little bit more about this path. All right? So, there's my projectile path, okay? And because of the way that it changes, sorry, did I point out to you the yellow triangles on the slug shooting lab yesterday? I know I talked to you guys, I know I talked to you about it, so we did it together. Did I point that out to you guys? Stand by. I know I should have this stuff. Oh, this is the wrong one. This is Yr1. Should have these things ready to go. I apologize. Not what I wanted to do. I think I pull up Internet Explorer. Okay, so I didn't hit the slug, obviously. That wasn't my intention of what I'm going to show you here. So if we look at the yellow triangles along the x-axis and along the y-axis, so what are we seeing about the yellow triangles along the x-axis? They're all about the same, right? Because what's not happening on the x-axis? No acceleration on the x-axis. That motion just continues. Whoever it was doing at the beginning keeps going and going and going. But on the y-axis, what are we noticing about those yellow ones? They get closer together on the way up, but then on the way down, what happens? They get farther apart. You can't tell the difference there, because like we talked about, the up trip and the down trip for something under the influence of gravity look exactly the same. So those yellow triangles along the left-hand side actually are two triangles piled up on top of each other, one to represent the up trip and one to represent the down trip. The end result of this, one variable changing at a constant rate, one variable changing at an inconstant rate, one side accelerating, vertical acceleration, horizontal non-acceleration, gives us this parabolic path. All right? So now, we got to go back into the memory banks of math class, right? What do we know about a parabola? Say again? Same on both sides. We say that if we use a fancy math term, that means that the parabola is symmetrical, right? It's symmetrical around a central axis, right? There's one spot up at the top, right? And then both sides are exactly the same, okay? Good there? That means there's a couple of things that are true about our parabolic flight of a projectile that we can use to our advantage, right? So, turn your Apple book to page it's the end of chapter 4. Page 138. Page 138. On page 138, there is a conceptual example 4.13 right in the middle of the page. And if I was a good teacher recording class, I'd have it up on the screen right now, but I'm not, so I don't. Okay. All right. So it says, you throw a friend You throw a ball to a friend with an initial speed of 10 meters per second. Your friend catches the ball at time t at the same level from which you threw it. Referring to the figure below, which of the plots, 1, 2, or 3, best represents the speed as a function of time? Okay? So, first thing, what do we notice about all three of those plots? Very similar to a parabola, all three of those plots, 1, 2, and 3, are all what? They're all symmetrical, and that's good. Okay, so we can't eliminate any of the plots based on that fact. All right, but let's talk about this plot. Right, it's a horizontal motion and it's a vertical motion occurring at the same time. The horizontal motion really doesn't tell us anything because nothing changes horizontally, but things do change vertically, right? For instance, when we threw the ball up in the air, just straight up in the air, right? What did we say happens to its speed? What happens to the speed of the ball as we throw it up in the air and we come back down and catch it? It decreases as it goes up, and it increases as it comes back down. Good. That eliminates one of the plots in that conceptual example, right? That means that which plot cannot represent the speed of the ball as you throw it? Number 1 is what's happening to the speed in number 1. It goes up and then comes back down. And that's not what happens to the speed of this ball, right? All right, but one other thing that's really important in terms of identifying certain parts in this motion, right? John, slows down and speeds up, but what else very important happens with it? Go ahead. Okay, so number 1, what's happening to the speed at the very beginning of plot number 1? It increases, but we said that when you throw something in the air, what happens to its speed? It decreases, right? So if the first thing that happens to that speed graph is it gets bigger, that's not representing what's happening when something's flying through the air. Okay? Now, next, right? What happens so Sean, the ball slows down on the way up, speeds up on the way down. No, I'm asking you another question. What also happens at the top? Stops. Okay? Now, that might lead you to think, which graph are we looking at? Which plot does that point to? Well, what happens to plot number 3 at the halfway point? The speed becomes what? 0. But that's true when we throw the ball straight up and straight down, right? But is that true when we throw the ball at an angle? We train concussion. I got it under control. When it reaches its highest point in that graph that we have up on the board, is the speed 0? Not. Because what is it always doing? Moving horizontally. So even though the top of the motion, its vertical velocity stops, it's still moving horizontally. So the speed of the ball is never 0. Does that make sense? So that means which plot represents the speed of the ball as it's flying through the air. 2, notice it reaches a minimum value on the x-axis at 1/2 t. As long as we catch it at the same level that we throw it from, it's going to take half of the time to go up and half of the time to come down. Just like when we throw the ball straight up into the air. Does that make sense? So these are symmetrical things that we can use to identify certain points in the flight of the projectile and use them to fill in numbers in the chart that we need to solve for whatever we're trying to solve for. Okay? So tomorrow, we'll do some more practice problems that identify certain parts of the flight of the projectile, and then plug numbers into those equations to get what we need to get to. Okay?